Are you interested in urban traffic safety and its effects on urban planning? Our summary today works with the article titled Intelligent Transport Systems for Sustainable Smart Cities from 2024 by Mohamed Elassy, Mohammed Al-Hattab, Maen Takruri, and Sufian Badawi, published in the Transportation Engineering Journal. This is a great preparation to our next interview with Brett Ferrin in episode 364, talking about how we are all responsible for traffic safety. Since we're investigating the future of cities, I thought it would be interesting to see intelligent transport systems and their role for the future of cities. This article presents intelligent transport system technologies and their effect on systematic traffic flows, safety, and environmental sustainability.
What is the future for cities? Do you want to learn more about them? Do you want to know how others think about them? Do you want to be part of the conversation? Then this is the right place.
Welcome to today's What is the Future for Cities podcast and its research episode. My name is Fanny, and today we will introduce a research by summarizing it. The episode really is just a short summary of the original investigation, and in case it is interesting enough, I would encourage everyone to check out the whole documentation. This conversation was produced and generated with Notebook LM as two hosts dissecting the whole research.
Today, we're diving into intelligent transportation systems, or ITS. These are really fundamentally reshaping how our cities handle mobility. We're talking about technologies like van nets, vehicular networks, sophisticated smart traffic lights, ITL, and even algorithms that predict traffic flow. These aren't just futuristic ideas anymore. They're critical tools cities are using right now to get safer, more efficient, and hopefully more sustainable. But this rapid transformation brings up a really central question, one that comes directly from the material we're looking at. When we evaluate ITS success and decide how to push forward, where should our main focus really lie? Should it be on the proven, tangible gains we're seeing in sustainability and efficiency? Or do we absolutely have to prioritize the critical and, let's face it, ongoing challenges around system security and just basic reliability? I'll be taking the position that the proven, measurable gains, the efficiency, the safety, the sustainability improvements, these must remain the central reason and focus for rolling out ITS. The results we're already seeing are frankly too important to let security worries hold progress. Security is critical, yes, but maybe it's more of an ongoing maintenance issue.
And I'll be arguing, from a slightly different angle. Focusing purely on those outcome metrics, saving minutes, cutting carbon, it feels a bit dangerous to me. The sheer complexity and our growing reliance on these networked, interconnected systems mean that the systemic security and reliability risks, they have to be rigorously prioritized first. Otherwise, the long-term, trustworthy viability of these incredibly complex systems people's lives depend on, is really in question.
Okay, the case for prioritizing the gains we're actually seeing rests on some pretty overwhelming empirical evidence. These systems are solving core urbanization problems today. We're seeing measurable improvements in cities, not just theoretical promises on paper. For instance, research consistently shows that effective ITS traffic management can drastically cut travel times. We're talking potentially up to 25%. Just think what that means for an average person's day. Less time stuck in traffic, more time for other things. And crucially, these systems directly help with sustainability goals. They can cut greenhouse gas emissions by around 15, maybe 20%, simply because vehicles aren't idling as much. And we have specific city examples that back this up. Look at Los Angeles. When they implemented their intelligent traffic light system, which dynamically coordinates signals across hundreds of intersections, they saw a 16% reduction in travel time and a 12% reduction in stops at lights. These aren't small adjustments. They're real, measurable improvements to traffic flow and consequently air quality. Plus, the industry itself is getting behind this. Major car manufacturers, BMW, Toyota, Audi, you name it, they're proactively integrating V2V, vehicle to vehicle, and V2X, vehicle to everything communication. They see ITS as foundational, a necessary step for safety and, of course, for the future of autonomous driving. So our focus really has to be on using these proven tools to meet urgent goals. like, say, Copenhagen aiming for carbon neutrality by 2025, or Dubai targeting 25% autonomous travel by 2030. These goals are being actively helped along by ITS.
I approach it differently, focusing just on those impressive outcomes, travel time saved, carbon reduced. It kind of obscures a really fundamental systemic risk. The underlying platform for these smart systems is frankly inherently fragile. There are basic security and reliability weaknesses, and if we don't address these as a prerequisite, they really threaten the whole ITS ecosystem. Failures here could cost far, far more than any efficiency gain provides. The material makes it pretty clear that the deep integration of wireless tech, things like DSRC, that's dedicated short-range communications, or the newer cellular V2X, well, it just opens the door to severe security risks. We could be looking at attackers exploiting vulnerabilities to get remote access to the entire vehicle network. That means compromising cars, infrastructure, or potentially both. Specifically, think about VANETs, these networks of moving vehicles. Their decentralized, sort of ad hoc nature makes them uniquely vulnerable to attacks on data authenticity. Take the Sybil attack, for example. This is where one bad actor pretends to be dozens, maybe hundreds of vehicles. It could flood the network with false information, reporting fake traffic jams, or worse, a non-existent hazard on the road. That could directly cause gridlock, wiping out all those efficiency gains you mentioned, or much worse, actually cause accidents by tricking automated safety systems. And we can't ignore the sheer software complexity. Millions of lines of interconnected code. This naturally introduces classic vulnerabilities, things like injection holes, buffer overflows. To actually guarantee the public safety that ITS promises, we have to prioritize foundational security analysis and reliability prediction.
Now, this involves some complex-sounding methodologies, things like hybrid fuzzy ANP topsis or unified neurofuzzy approaches, but their purpose is straightforward. They're mathematical tools we use to try and foresee software bugs and security flaws before they cause failures out on the road. Security isn't just a feature you patch in later. It has to be the bedrock of a trustworthy system.
I appreciate the intellectual honesty about the system's weaknesses, but we do need to put the risk in perspective compared to the benefits we're getting now. I'd argue the success of ITS is best measured by its actual impact on solving critical urban problems, reducing congestion, cutting journey times, limiting environmental damage. These tangible results are really the only metrics that justify the huge resources being poured into ITS deployment globally. And if we're talking about what makes this possible, the integration of 5G is pivotal. It gives us the high-speed, ultra-low latency communication needed for true real-time operations. This lets complex systems like those intelligent traffic lights react instantly to changing conditions, maybe adjusting signal timings immediately when an accident is detected miles ahead, preventing huge backups. This is a necessary leap forward that drives efficiency and improves quality of life right now. We shouldn't halt that progress chasing theoretical vulnerabilities.
That's an interesting point about 5G enabling real-time reactions, but I'd frame that technological advance differently. Focusing only on outcomes like speed and less congestion ignores how achieving that efficiency is fundamentally tied to massive security challenges, especially around, well, privacy. If real-time data collection makes things efficient, it simultaneously creates a huge vulnerability for personal data, for mobility patterns. Every time an ITS platform tracks a vehicle to optimize flow, it's tracking an individual. We're essentially trading vast amounts of personal data, often without full awareness, for sometimes marginal efficiency gains. And without truly robust security, that data is just ripe for misuse. But even setting privacy aside for a moment, system integrity is just paramount. You mentioned 5G helping react quickly to a real accident. Okay, but what happens when that Sybil attack I mentioned generates false hazard warnings across the network, pretending an accident happened? All those immediate efficiency gains, gone. Instantly replaced by unnecessary congestion, maybe even panic, and a high risk of secondary accidents caused by those false alarms. The system must be trustworthy before it can be efficient. That's why we have to invest equally, perhaps even more, in robust authentication protocols defined by standards like IEEE 1609, which sets out the security services and constant network monitoring to detect and stop rogue nodes before they poison the whole system. And I want to stay on that point of system integrity by looking at how fast things are developing. I'm sorry, but I just don't buy that the industry security practices are keeping pace. Let me explain why.
The incredibly rapid adoption of cutting-edge tech, V2X, 5G, countless IoT sensors, yes, it's great for rolling out new features, but it massively compounds the difficulty of finding and fixing fundamental software flaws. The auto industry's software development cycles are lightning fast now, driven by getting new features to market immediately. This often outruns the kind of rigorous security auditing and architectural design that's needed. The sheer complexity here demands foundational security measures. These need to be defined by robust, universally adopted standards, like the full IEEE 1609 suite, to prevent unauthorized access and data tampering before we deploy these systems at full scale to the public. If we prioritize speed to market over a thoroughly vetted security architecture, we are, in essence, building incredibly complex systems that are almost designed to fail, potentially spectacularly, endangering the very people we claim to be protecting. It feels like sacrificing long-term stability for short-term gains.
Hold on, I really have to push back on that line of reasoning, because the immediate measurable safety benefits we get from advanced communication justify their swift integration. Are you seriously suggesting we should deliberately slow down the deployment of technology that is demonstrably saving lives today until every single theoretical vulnerability is found and patched? We cannot let the theoretical risk of a future cyber event paralyze us when we know these systems are preventing accidents and fatalities right now. That trade-off feels, frankly, morally unacceptable. Think about concrete examples. Vehicle-to-pedestrian, or V2P, communication at interceptions. It's facilitated by these high-speed, low-latency networks you mentioned. It significantly cuts the risk of accidents by sending real-time warnings to both pedestrian smartphones and nearby vehicles. Estimates suggest a huge portion of certain types of crashes could be avoided if travelers just got a warning a few seconds earlier. Similarly, look at the e-call systems mandated across Europe. They rely entirely on VANETs and cellular networks, like 5G, for rapid emergency response. This system automatically sends the precise location and status of a crashed vehicle to emergency services. This is absolutely critical for saving lives, especially considering global accident fatality rates. If we delay these crucial life-saving features because we're afraid of future vulnerabilities, we are actively costing lives now. So I challenge you, if industry standards like IEEE 1609 are already mandating security services and protocols, what concrete evidence do we have that their current deployment is fundamentally inadequate for handling real-world threats today?
Okay, that's a strong counterpoint on immediate safety, and I absolutely agree that systems like e-call saving lives is paramount. However, the evidence suggests that if the foundation is flawed, those very life-saving features can become attack vectors themselves. My argument isn't to stop deployment entirely, but rather that the investment in the foundational security architecture must be equal to, if not greater than, the investment in the features themselves. The source material highlights the critical need for robust software maintenance. This is an ongoing, often under-resourced security concern. Every time a new safety feature is added, the system complexity increases, and therefore the attack surface grows. Current industry standards, while essential, might not be adapting quickly enough to this exponential growth in software complexity. Think about it. Just one successful, large-scale remote compromise, which becomes more plausible as systems rely more heavily on complex V2X comms, could instantly negate years of safety gains. That's the systemic risk we just can't afford to ignore. And managing it requires continuous predictive vigilance, not just reactive patching.
All right, let's maybe shift focus slightly towards foresight and planning, which is obviously central to long-term success here. If we're talking about future-proofing these systems, I believe the answer lies in predictive mobility. Mobility prediction is a really crucial ITS application. It ensures both efficiency and safety because it allows the system to respond proactively to traffic, not just reactively. Predicting where vehicles are likely to go helps optimize traffic light timing, allows for dynamic lane assignments during peak hours, and it's absolutely essential for advanced driver assistance systems, ADAS, to anticipate collision risks before they even happen. For the end user, this technological foresight is really the key to creating transportation systems that feel seamless, efficient, and meet the growing demands of our cities. This focus on forecasting movement lets the whole infrastructure anticipate demand and hopefully prevent congestion before it even starts.
That's a compelling argument for predicting movement. But have you considered that predicting system reliability is arguably just as important, if not more so, than predicting mobility? Yes, mobility prediction helps move vehicles efficiently when the system works. But if the system itself fails because of an undetected software error, well, the results can be immediate and devastating. Think about system failures caused by hidden software flaws, maybe a buffer overflow in a critical traffic control algorithm. This could instantly disrupt traffic flow across a whole area, cause massive, unmanageable congestion, and introduce serious safety risks on a citywide scale. So we must allocate significant resources towards industrial reliability prediction. That means using methods to foresee and mitigate the impact of potential system faults, ensuring consistent, trustworthy operation day in, day out. Your very point about relying on complex prediction algorithms for traffic flow actually highlights the inherent potential instability of complex ITS software. These algorithms are intricate. They necessitate advanced methodologies like the unified neurofuzzy approach you might read about, which, put simply, uses computation to model potential system failure rates and predict software bugs proactively. If we can't be reasonably sure the system will stay operational, then the efficiency it promises is just hypothetical, isn't it?
I think we fundamentally disagree on where the inevitably limited resources should be prioritized. The evidence, as I see it, is clear. The successful rollout of ITS tech has already delivered quantifiable, sometimes dramatic improvements in sustainability and efficiency in cities worldwide. We see it in reduced travel times, lower emissions, better road safety through things like intelligent traffic lights and V2X communication. The focus really must stay on capitalizing on these tangible, real-world gains to meet the pressing urban mobility and climate challenges we face today.
I agree, the pursuit of efficiency and sustainability is absolutely vital, but it simply cannot outpace the foundational needs of security and reliability. The inherent vulnerabilities we know exist in decentralized VANETs, the ever-growing complexity of all this integrated software, and the persistent threat from sophisticated cyber attacks. All this demands a dedicated, rigorous, and ongoing focus on mitigating vulnerabilities, on robust authentication, and on comprehensive reliability prediction frameworks. That's the only way to ensure the long-term trustworthy operation of these critical, life-dependent systems.
So while the efficiency and safety benefits of ITS are, I believe, unequivocally clear and already present, you've certainly underscored skillfully that the path toward truly resilient and sustainable smart cities absolutely involves grappling with these equally complex technological and security trade-offs, which are well documented in the material itself.
Indeed. The discussion really highlights that a truly smart city system has to both demonstrably effective in achieving its goals and dependably secure in its foundation. Getting that balance right is the core challenge for the long term.
What is the Future for Cities podcast?